In this section, we will talk about ionic compounds that include polyatomic ions. First, let's talk about what a polyatomic ion is. A polyatomic ion is a group of atoms bonded together that have a charge, and they act or behave like a single unit or ion in the compound. They're not free compounds, and like other ions, they're not found free in nature. They're found combined with other ions. So here are some examples. Sulfate is a group of atoms, 1 sulfur and 4 oxygens bonded together, and as a unit that has an overall 2- charge. Nitrate is a group of atoms, 1 nitrogen and 3 oxygens, all bonded together that overall have a minus charge. And carbonate, 1 carbon and 3 oxygens, all bonded together that overall has a 2- charge. Those parentheses are used to keep those atoms together, to show them as a group, and nothing within those parentheses can change. Most polyatomic ions contain oxygen atoms and have endings like ite, ITE, or ate, ATE. In those pairs with ite and ate endings, the ion with fewer oxygen atoms will have the ite, ITE ending. For example, sulfite and sulfate, nitrite and nitrate. The ITE ending has fewer oxygen atoms than the ATE ending. So just to show you an example, sulfite has 3 and sulfate is SO4. That, okay? The suffix doesn't indicate the actual number of oxygen atoms because nitrite and nitrate, so nitrite is NO2 minus, nitrate is NO3 minus. Okay, so and I see I made a little mistake here. Sulfite and sulfate both have 2 negative charges. Okay, so just to see here, the ite ending has 1 less oxygen than the ate ending, but the suffix doesn't indicate the actual number of oxygen atoms, just the trend in one having fewer than the other. Okay. Here is a list of common polyatomic ions. There are more, but this list is the most common and would be the most helpful for you to know and memorize. Most polyatomic ions are anions, and you can see starting at the top from acetate, carbonate, nitrite, and nitrate, which we just talked about, hydroxide, phosphate, sulfate, and sulfate, which we talked about. But 2 of them here shown are cations, and that's hydronium, H3O plus, and ammonium, NH4 plus. And they will act as the cation in an ionic compound, replacing the metal in the ionic bond. So they would come first, right? When we talked about like sodium chloride, where the sodium would come first because that was a positive charge. If hydronium or ammonium were in the compound, they would replace that metal and come first in the ionic formula. The rest of them, as I mentioned, are negatively charged and would replace the nonmetal. How do we write the names of these compounds that have polyatomic ions? They're called ternary ionic compounds because they contain 3 or sometimes more than 3 atoms, but 3 atoms. And it's an indication that a polyatomic ion is present. So ionic compounds with polyatomic ions contain 3 or more different elements due to the presence of those polyatomic ions. Just as in binary ionic compounds, the name of the cation is given first, followed by the name of the anion. And so we just name the anion. And so that often means that we have that ite or ate ending. So let's look at these examples. Ca, we know, is just calcium. And then the polyatomic ion here is CO3. CO3. That's carbonate. So we just name the ion. Here we have Cu, copper, and then NO3 is nitrate, copper nitrate. But copper is a transition metal, so we have this 2. I wanted to show you something also because I don't know if this was clear earlier. How do you get the charge of a transition metal when it's in a compound? What you have to do is you just reverse your crisscross. So you bring the 2 up here. And then, of course, there's a little imaginary 1 here. So what this says is that copper is 2+, and then that nitrate is 1-. So just as a reminder, this 2 is what ends up as your Roman numeral. So copper 2 nitrate. And then the last one, sodium is Na, and then SO3 is our polyatomic. That's sulfite, so sodium sulfite. Okay. So we're just naming the cation, naming the anion. Writing formulas for ionic compounds that include polyatomic ions is the same as what we showed before for a binary compound. So let's write the formula for lithium phosphate. We start by writing the symbol and the most common charge for lithium, Li, with a 1+ charge. Now, phosphate is a polyatomic ion. It's a group of atoms, 1 phosphorus and 4 oxygens that have an overall 3- charge. Okay. Then we crisscross those charges. So the 3 will come down here, and the 1 will come down here. And again, I'm grouping these atoms together to make sure that I'm remembering they act as a unit. And I can rewrite those charges as subscript. So I have 3 lithium atoms and 1 phosphate ion. Okay, so 3, I think I said atom, 3 lithium ions and 1 phosphate ion. And then reduce the subscripts as necessary. Now, I was able to get rid of the parentheses here because I only had 1. And I don't need to write a 1. But if I had a 2 here, or 3, or any other number, I would just keep the parentheses to keep the polyatomic ion in a group if there are multiple. All right, let's look at another example and write the formula of manganese 3 carbonate. Manganese 3 carbonate. So we start with the symbol for manganese, Mn. And remember that this 3 in Roman numeral tells us the charge. So that's that 3+, right? And then carbonate is a polyatomic ion. If we weren't sure, that 8 ATE ending would tell us that, right? Carbonate would be CO3 as a group with an overall 2- charge. Then we crisscross the numerical values of the charges, bring the 3 down to the right and the 2 down to the left. Now, when you bring this 3 down, you can't just write a 3 over here. Then it just is confusing, right? It doesn't show that you have 3 carbonate ions. So that's why we put these parentheses here and bring the 3 down and the 2. And so we have Mn2 CO3 in parentheses 3 to show that we have 2 manganese ions and 3 carbonate ions. So we have to keep that polyatomic ion in parentheses as a group because there are more than 1.